Yeah, this is module 4. The DTFT what you had seen, that also was module 4 only. In module 4, we have DTFT as well as DFT, the Fourier transforms. Fine. Now DTFT is for discrete time and Fourier transform is for continuous time. Sometimes to be precise, people call it as CTFT also. What is CTFT? CTFT is continuous time Fourier transform. This is discrete time Fourier transform. But saying discrete time is must for DTFT, whereas for continuous time, if you just write FT, it is understood that it is CTFT. It is similar to your Fourier series also. In Fourier series, if we just say Fourier series, it is for continuous time signals. Okay, for discrete time signals, it is discrete time Fourier series, which was discrete time Fourier series was not there in your syllabus. So we have just covered continuous time Fourier series. Understand that? And in when we were discussing DTFT, also I've told you. Okay, DTFT and FT are applicable for non-periodic signals. This is for DTFT is for non-periodic discrete time signal, and Fourier transform is for non-periodic continuous time signal. Understand? Whereas Fourier series is for periodic signal. Understand? I had asked you one question in the internals. Okay. What do you think the speech signal should? If you have a speech signal, what which transform would you apply for that? Okay. So for that, what should be your answer? See, speech signal is a continuous time signal. Okay. And is it periodic or non-periodic is the next question we need to ask. So speech is non-periodic. Speech is non-periodic continuous time. So which is suitable for non-periodic continuous time? So Fourier transform is suitable. Why DTFT is not suitable? Both are for non-periodic, that's fine. But DTFT is not suitable for speech because speech is not discrete in time. Speech is continuous in time. That's why Fourier transform is applicable for the speech. So this is the justification that you should have given after saying that it is Fourier transform. Fine. So see, that's why it is being told very clearly. This is applicable for continuous time, non-periodic signal. Okay. It could even be called as CTFT to be precise. Otherwise, just saying FT means it is continuous time Fourier transform. Fine. So let's go on with the equation. See, a non-periodic continuous time signal x of t can be expressed as, it is expressed as this. Okay, as was the case in DTFT. Okay, this is the time domain signal, this is the frequency domain signal. Understand that? Yes. Now, how we used to denote this was x of n earlier in case of DTFT because we have to deal with discrete time signal. Okay, and this is the spectrum, this is the uh, frequency domain signal. In frequency, how we were denoting our frequency domain signal, that is the spectrum, that is what that was being denoted as x x of e power j omega. That omega was ohm omega. Okay, so it is this w omega. Here e power j omega is not given, just j omega is given. Maybe it is just to differentiate between the spectrum of the continuous time signal and the discrete time signal. Understand that? So this is what, how does the spectrum looks like? It looks like this, where the spectrum x of j omega is given by this. And as is the case in every transform, this x of t and x of j omega, they're called as transform pairs. That means if you have the time domain signal, you can obtain it. If you have the frequency domain signal, sorry, you can obtain the time domain signal. Or if you have the time domain signal, you can always obtain the frequency domain signal. Okay, that's why they are called as transform pairs. That is what is being called as being said here. X of j omega is a frequency domain representation of time domain signal x of t and are called transform pairs, which is represented like this. Okay. Now, unlike x e power j omega, this is what I was telling. This is what is this? This is this spectrum in DTF. This is DTFT of a signal. This is FT of a signal. This is discrete time Fourier transform of a discrete time signal. This is continuous time Fourier transform of a continuous time signal. So what is the difference between these two? See, x e power j omega, though x of n was non-periodic, the spectrum of non-periodic x of n was periodic in nature. But here, the continuous time spectrum, the spectrum of continuous time signal is what? Non-periodic. This is something that one should understand. I repeat again, this is the spectrum of the non-periodic signal, discrete non-periodic signal. This is the spectrum of continuous time non-periodic signal. So this is DTFT, this is FT. DTFT was periodic in nature, though x of n was non-periodic. Okay, the spectrum of non-periodic x of n was what? Periodic in nature. Whereas here, the spectrum, okay, of x of t is non-periodic. So this is something one should understand. Fine. Now, x of j omega exists only if x of t is absolutely integrable. This was seen in the other transform also. If it is absolutely integrable, what is being absolutely integrable? When would this be possible? When would this spectrum available, or it is possible? It is possible only when this x of t is absolutely integrable. That means if you integrate this x of t over this period, okay, that integration should give you a value which is less than infinity. That is what is called as absolutely integrable. If it is infinity, then the spectrum does not exist, is what is the meaning of it. Fine. So I think let's move on with the problems. Very similar problems, not at all difficult. Very similar problems we'll be seeing. Okay, you will not have any problems to solve this. Fine. Obtain the Fourier transform of the signal given by x of t equal to e power minus a t u of t. Okay, there, if it is DTFT, this signal should have been given as a power n u of n. Understand that? If it is discrete time, this signal exactly looks like a power n u of n. Which signal is this? This is decaying exponential signal. Decaying exponential signal. Understand that? In discrete time, it looks like a power n u of n, whereas here it looks like e power minus at u of t. Fine. A is greater than 0, it is saying. Fine. So draw its magnitude and phase spectra. Let's see. So this is the equation. This is the equation we need to use for finding out the Fourier transform. Find the Fourier transform means what? Fourier transform is actually the frequency domain signal, okay, which is denoted by this, and it is given by this. What is the difference between the spectrum here and this spectrum? This spectrum was having summation, okay, and this spectrum is having integration. Remember this. So in DTFT we were doing summation. That's why this DTFT is very similar to the Z transform. Whereas in continuous time Fourier transform will be integrating. Okay, will be integrating. Fine. That is the difference. Now x of t is the signal given. Fine. X of j omega is what we are asked to find out. Fine. Now see here, x of t is substituted, okay, and after substitution this u of t is taken as 0 to infinity. Okay, this u of t, why it is taken from 0 to infinity, I think I should not be explaining you all this now, because you've been seeing throughout the semester. Okay, and you'd be very comfortable if I don't write that here. Okay, and then say it is 1 from 0 to infinity. So u of t is 1 from 0 to infinity. That's why it's taken from 0 to infinity here, making u of t 1. Okay, and this exponential is written there. Fine. and there are again two exponentials which needs to be clubbed. Okay, after this you have to just integrate, and easiest of the integration is for the exponentials. Okay, so the integration of this would be the same exponential. Okay, and since it is being integrated with respect to the time, the coefficient of the time should come in the denominator, that is minus a plus j omega should come in the denominator. Okay, once you integrate, just apply the uh, limits of integration and you would find your spectrum. Okay, the spectrum of continuous time signal to be this. These are all standard transforms. Why they are standard transforms? So we see these Fourier transform or DTFT or Fourier series all for the standard transform, and remembering those standard transforms we try solving the complex problems. Okay, so this is how we solve the problem. Just remember this equation. Not in every problem I'm writing this. Okay, so in place of x of t, maybe in the coming problems I'll just substitute this. Fine, directly whatever x of t is given, I'll just be substituting here. So just remember this equation. Fine. Now let's move onward. The next problem. Now again, this is not new to you. Okay, what was the difference between the previous problem and this problem? In the previous problem it was e power minus 80, and since it was e power minus 80, I had to tell this e power minus 80 exists from where to where. It exists from 0 to infinity, that needs to be told. That's why this u of t is accompanying this exponential. Whereas in this problem what's happening, there is no u of t at all. Everyone understand? What does that mean? That means that this magnitude t, okay, clearly indicates this x of t ranges from minus infinity to plus infinity. Okay, so we can write this using the unit step functions. Okay, so you'll have one unit step ranging from minus infinity to 0, another unit step ranging from 0 to infinity. It's not like your discrete time, where in the negative side you will have a unit step ranging from minus infinity to minus 1. No, it goes from minus infinity to 0 and again from 0 to plus infinity because it is continuous time. Okay, so in discrete time you need to be little careful because you'll go from minus infinity to minus 1, then you start from 0 to infinity. Understand that? Okay, so how does it look like? This is how it is going to look like. See, it is u of minus t, whereas in discrete time we used to write it as a power n u of what? U of minus n minus 1 we used to write here. Okay, now see us, since this is on the negative side, this this t has to have negative sign. This t has to have negative. When you attach this t with the negative sign, this negative sign with a goes off. So it's minus a into minus t. So that becomes 80 by attaching this minus sign to t, because you're on the negative side. It is from minus infinity to 0. Okay, so we have another exponential which goes from 0 to infinity. And why this minus is retained there? Because now we are talking about plus t, not minus t. So this minus would retain, whereas that minus was cancelled because of negative t. Here, because of the positive t, this minus is retained. Understand? So this again is something that we all understand. Fine. So let's be careful when we are doing this with continuous time signal and discrete time signal. There's a small difference which you all, I think, are aware of. Fine. Now, x of j omega is there, right? Yeah. This is what is the signal I was talking about. Okay. Now, this is the equation wherein I'll be substituting this. Okay. So where from the integration limit should be going for this term, it should be going from minus infinity to 0, and for this term it should be going from 0 to infinity. So that is what we're going to see now. Here it's from minus infinity to 0. Again, this u of minus t is not brought there because it's understood that u of minus t is 1 from minus infinity to 0. So that's eliminated. Okay, and similarly here it's from 0 to infinity, and from 0 to infinity u of t is 1. Okay, so that also gets eliminated. So we're left with again two entities here. Both in both the parts we have the exponential. Just club those exponentials, okay, and integrate again as we did in the previous problem. And this is what you're going to get by integrating and applying limits. Okay, uh, and if you just take the LCM, it's in a minus b, a plus b form. So they have taken it as a square plus b square. Okay, a square minus b square rather. Now what happens? A square minus b square, since j is there. Okay, j square would become minus 1. That's why this minus would a square minus b square. This minus would get combined with the minus we have from j square. Okay, that is how it becomes plus. Okay, so you just do this, you'll get fine. Very simple problems, provided you have understood your Z transforms, then your DTFTs or Fourier series. Very similar problems. Okay, no difference at all, except for yes, there in DTFT we were doing the summations. Here we'll be doing the integrations and the simple ones. Fine. Yeah, this is again a standard signal, that is delta of t. Fine. Uh, and as we can see, in place of x of t we have delta of t. Fine. Now which how do you uh, solve this integration? Okay, so this again is something that we have learned in the very first chapter, the properties of unit impulse function. Okay, if you go to the properties of unit impulse function, it was very clearly understood that there are properties like product property and shifting property, SIFT. So product property comes when this integration is not there. Okay, what is the product property if you take this? So it's delta of t into this exponential being evaluated where delta of t stands. Okay, delta of t is existing at t equal to 0. Okay, so that's why this needs to be evaluated at t equal to 0. That was what we saw with product property. But when this integration comes, it is shifting property in continuous time. Okay, so because of that delta of t exists at t equal to 0. Okay, since this exists at t equal to 0, this should also be evaluated at t equal to 0, and we get that to be 1. Okay, fine. So this is what is important. Now let's move on. In all the transforms, the transform of delta of t or delta of n is 1 only. Fine. Let's move on to this signal, wherein in the previous problem the signals were being given, okay, in mathematical form, whereas in this problem the signal is sketched. Okay, only that is the difference. Find x of j omega, again the same, and it is 1 from where to where? It is 1 from minus t to plus t along with this exponential which is there in the equation for x of j omega. Fine, just integrate this and apply the limits. Okay, integration of this is this. Okay, and we are applying the limits, and after application of limits it looks like this. And just arrange this in a proper form. That's it. Okay, and since this is something that we know, e power j omega t minus e power minus j omega t, along with this 2, there should have been 2j here. Okay, but that will compensate by having a 2 in the numerator. So it is sine 2 sine omega t divided by omega. Okay, so this is what we can do with this spectrum here. Fine. So this is all your trigonometric basics, and I hope you're all good with that. Fine. So let's move on with the next problem. That is e power minus 3t into u of t minus 1. Fine. Now, what is the range of u of t minus 1? From where to where u of t minus 1 goes? U of t minus 1 exists from, it is 1 from 1 to infinity. So it means that e power minus 3t is also ranging from 1 to plus infinity. So this is 1 from 1 to infinity. So when you multiply this signal with u of t minus 1, the range of this also would become 1 to infinity. So that is what we're going to see. Okay, so this is the equation. In this equation, e power minus pt is substituted in place of x of t, and u of t minus 1 is 1 from 1 to infinity. So that's eliminated. Fine, again, club the exponentials, integrate and apply the limits. Okay, and just try bring it to a proper form. We can move ahead, or we can stop somewhere where we think that is sufficient. Okay, it all depends on depends on the question. If they ask you to bring it to a proper form, particularly in your question, then we can bother about that. Otherwise we can stop it somewhere we think is fairly simplified. Fine. This is how it goes now. Now here you have, earlier we were having just one function of t, okay, along with u of t. Now there is another function of t. So this poses a challenge. Where does it pose challenge? You need to be good with your integration. Earlier only exponential used to be there. Okay, so integrating exponential is not at all a problem, but along with the exponential now t is going to come. So integration by parts is what we need to know, and hopefully you would all be comfortable doing that. Okay, so let's move on. So this is the equation that we always go with. Okay, to find the spectrum, that's x of j omega in place of x of t. Again, bring this. Okay, so since u of t is there, u of t is substituted as 1, since we are going from 0 to infinity, because from minus infinity to 0 it is 0. So this exists from 0 to infinity, so we consider it from 0 to infinity. Fine, just club the two exponentials. Okay, now the challenge is, as I told, this t. Okay, so this is integration by parts. Okay, applied the what, so that application of limits is not shown here, but it's solved. Okay, so you can go step by step, or you can solve yourself, because understanding the problem which somebody else has solved is something that's bothering. So instead it's easier we solve it, provided we know. Okay, so if we know that, we can solve it ourselves. Okay, so try do that with with every integration. That would be interesting also to get what we have got here. Fine. uh, Here, if it is just e power minus 2t without this t, this square will not be there. Okay, soon after t comes with the signal. Okay, so it would be 1 by this parameter, this square. Okay, that you need to know. If this t is not there, what if the t comes? What? Okay, so this is very similar things that we have been seeing. Okay, as far as the transforms are concerned. Fine. So this is another problem that I wanted to discuss. Okay. Again, this is all regarding the range from where to where it is. Now it's not the same signal throughout. It's one from my minus 2 to 0. This is minus 2 to 0, and this is minus 1 from 0 to 2. So accordingly you have to adjust your integrals. Fine. So this is x of t is 1 from minus t to 0, and x of t is minus 1. So that minus 1 is taken here. Okay. So x of t is minus 1 from 0 to 2. So the x of j omega would look like this. After substituting the equation for x of j omega. I'm not doing that. Okay. Just solve this. There is nothing much once we understand the signal and the range. Okay, so understanding the signal and range is what is important here from signals and systems point of view. Otherwise, it's just the integration and applying limits. Fine, just apply the limits. You will get to see this. Fine. Again, this is something that we can bring this in standard form. Okay, so that is what is done. So this along with 2 in the denominator would make it cos j omega. Cos, okay, here it should have been j2 omega. Here, j2 omega is there, right? So this 2 is missing here. This 2 is missing. Okay, and the denominator 2 is compensated here. Fine. So just remember, since it is e power j2 omega, okay, and e power minus j2 omega, here it should be cos j2 omega. Okay, that 2 is missing here. Make a point to add that 2 here. Fine, just simplification. You should not have problems regarding all that. Now again a similar problem. See the range from -1 to 0, x of t is 1. From 0 to 1, x of t is 2. From 1 to 3, x of t is -1. Simple problem. Just split your integrals into this 1, 2, 3 integrals we'll have. Okay. So x of t is 1 here. X of t is 2 here from 0 to 1. X of t is -1. That's why this minus has come here. So x of t is -1 from 1 to 3. Again, this is simple enough. Okay. Just proceed from here on. You would easily get this. Okay, I'm not doing because these are all simple steps. Okay, and anybody can do this. Those who have studied your M1, M2, M3, M4, M4 maybe you're studying. Okay, but you should not have problems solving all this, right? So not in detail, but you can manage, I believe. This again is another problem wherein the sketch is not given, but this is given, the signal is given. Yeah, the challenge is magnitude t. How to, this is what, if you just understand this, the problem is solved. Magnitude t is there. What to do with magnitude t? Yeah. What is the meaning of this? For t less than or equal to 1, it is this. Okay. For t greater than or equal to -1 also it is this. For t greater than 1, it is 0. For t less than 1, it is 0. What does that mean? Okay, let's see. So this ranges from -1 to 1. So t less than or equal to 1 and t greater than or equal to -1. So it's from -1 to 1. So seeing this, you should understand the range. This you need not have to bother because this is 0 for t greater than 1 and for t less than -1. For t less than -1 or t greater than 1. As it is, you take positive. T greater than 1. Another case is t less than -1. Here, t less than or equal to 1. Another case is t greater than or equal to -1. Okay, so that is how we need to read this. You have done that before, okay, and I've explained you again. Fine. Just try solve this yourself because this is what is important. Understanding that this x of t ranges from -1 to 1 is what is important. Okay, just do that, and I've given you the the answer directly so that you can solve it yourself. Fine, answer is there anyways. Okay, just analyze this and try to do it yourself. That will be a good exercise. Fine, and I hope we can stop here. Fine, we will